Since December 2021, the James Webb Space Telescope has unlocked various secrets of our universe. From providing newer images of galaxies previously captured by the Hubble Space Telescope to enlightening experts on supernova remnants and peering into the early universe, the spacecraft has already made remarkable discoveries. In its latest observation, the powerful Webb telescope has captured a new deep-field view of the universe, showcasing some of the farthest reaches of space. In Webb's image, the hundreds of objects visible are galaxies among the black ether of the cosmos, each teeming with stars and planets. Many are spirals, similar to our Milky Way galaxy, while the deepest ones appear red as the expanding universe has stretched their light into longer wavelengths of red light. This view, looking back at galaxies billions of years ago, reveals several ancient galaxies and the black holes at their centers, merging just a couple of 100 million years after the Big Bang created our universe. At the start of everything, the cosmos grew at a truly terrifying rate, expanding exponentially. Space begat space in a relentless cycle, stripping reality of all form and creating a tenuous, near-featureless void. If you could have sat on an atom, though there were no atoms yet, and gazed out at the rapidly expanding universe, you would have seen nothing but a freezing, suffocating darkness. The remorseless stretching of space would have carried all other objects far out of sight, faster than the speed of light, beyond an unreachable horizon. Paradoxically, as space expanded, the world visible to any would-be observer shrank to a tiny, inescapable nutshell, binding every speck within its own isolated sphere of nothingness, separated from all other such specks by an ever-growing void. This age of extreme expansion has been given a rather mundane name: inflation. How long inflation went on, we do not know. It could have been a mere instant or an eternity. In all probability, we will never know, nor are we likely to discover what, if anything, came before it took hold of the cosmos. Any traces of earlier epochs have been erased by the growth of space. But we do know that at some point, inflation ended, and as it did, the universe roared into being. The force that drove inflation dwindled, and its power birthed innumerable particles, filling the gasping void with a searing subatomic fire, the primordial plasma from which all objects in the cosmos would later form. From darkness came light. Within a trillionth of a second, the forces of nature came into existence, and with them, the first and greatest blaze of light in cosmic history. Though inflation had ended, space was still expanding, albeit at a less ferocious rate. As the cosmos continued to grow, the primordial fire began to cool. Elementary particles, the building blocks of everything yet to come, fused to form the hearts of the first atoms. Over the next few minutes, the nuclei of the first chemical elements were forged: hydrogen, helium, and lithium. For around 380,000 years, the infant universe was filled with an incandescent fire, cooling slowly as space continued to swell. Then, at a critical moment, the temperature dropped low enough to allow electrons to wrap themselves tightly around wandering atomic nuclei, forming the first whole atoms. At this moment, the primordial flame went out, and darkness fell throughout the cosmos. A long dark age began. For hundreds of millions of years, the universe was filled by a warm hydrogen fog. But in the darkness, the first seeds of structure were gathering. Slowly at first, then faster and faster, hydrogen and helium were drawn under gravity into ever thicker clouds. As these clouds grew dense, they also grew hot. At last, somewhere in the unsearchable reaches of space, the pressure at the center of one cloud became so intense that it ignited a nuclear fire, the spark of the first star. Light flooded back into the universe, and the dark age ended with a cosmic dawn. Soon, the universe was filled with stars, bright points of light in the slowly expanding dark, gathered in the first galaxies. They forged chemical elements never seen before: carbon, oxygen, nitrogen, iron, and many more, scattered through space as these first stars died in blazing supernovas. From their glowing embers, new generations of stars were born, and yet more elements were forged in a continuous cycle of birth, death, and rebirth. Around 9 billion years after the cosmic dawn, in an outer spiral arm of one of the hundreds of billions of galaxies now spread through space, a new star flickered into light. About it circled a fleet of worlds, and on one rocky sphere, Earth, matter somehow came to life. Under the guidance of dumb physical forces, atoms arranged themselves into ever more complex organisms that grew, multiplied, and evolved. For billions of years, the pale blue orb teemed with living things. Species emerged and perished, and the dance of evolution went on until at last, humankind stood on the surface of the Earth, gazed up at the stars, and wondered. This story of the cosmos, its origins, and its history has been gradually pieced together over centuries by the collective effort of thousands of people. The fact that modern science allows us to speak with such confidence about events so remote in time and space that they defy imagination is surely one of the greatest achievements of our species. Particularly when you consider that this story was assembled by peering and prodding at the universe from a rather restricted vantage point on the surface of an insignificant little rock hurtling through space. But while we know how the universe began, the data we have amassed in both particle physics and astronomy tell us that we still only know about a tiny fraction of the universe. Looking at the sky, we observe that on the largest scales, matter is organized into galaxies and clusters of galaxies. Galaxies contain stars, planets, and gases, all the visible universe. The Earth, Sun, stars, and galaxies, everything that makes us, is made of protons, neutrons, and electrons bundled together into atoms. Physicists have developed an impressive body of knowledge about the fundamental particles and forces that characterize the ordinary matter around us. Centuries of discovery have shown that apples fall from trees for the same reason that the Earth orbits the Sun and that the Earth is not at the center of the universe. It is a simple and elegant picture. The quest to answer the most basic questions about the universe has reached a singular moment. Astrophysical and cosmological observations have revealed that our picture of the universe is incomplete. Perhaps one of the most surprising discoveries of the 20th century was that ordinary matter makes up less than 5% of the mass of the universe. The rest of the universe appears to be made of a mysterious invisible substance named dark matter and a force that repels gravity known as dark energy. The exotic unknown substance named dark matter doesn't appear to absorb, reflect, or emit light, rendering it invisible. Since dark matter interacts very weakly with normal matter, its existence is inferred due to its gravitational effects on galaxies. Its fingerprints appear only when we look to the sky at the galactic and supergalactic scales, at about 10 million times the distance between the Earth and the Sun. According to physics, stars at the edges of a spinning spiral galaxy should travel much more slowly than those near the galactic center, where a galaxy's visible matter is concentrated. But our observations show that stars orbit at almost the same speed regardless of their distance from the center of the galaxy. This puzzling result only makes sense if we assume that the boundary stars are feeling the gravitational effects of an unseen mass, a halo of dark matter enveloping the galaxy. The existence of dark matter could also explain some optical illusions that astronomers see in the deep universe. For example, there are pictures displaying strange rings and arcs of light. These can be explained if the light from distant galaxies is distorted and magnified by massive invisible clouds of dark matter in a phenomenon known as gravitational lensing. The radical conclusion that the universe is filled with invisible and nearly undetectable matter can be compared to Copernicus's identification that the Earth is not the center of the solar system. We have established that we don't know what most of the universe is made of. Just like ordinary matter, dark matter also originated from the Big Bang. The amount of dark matter produced in the Big Bang has influenced the evolution of our universe. Similar to ordinary matter, dark matter isn't distributed across the universe evenly. Areas of the universe that had slightly more dark matter, and so more gravitational pull, attracted more matter, leading to the creation of the first stars and galaxies. The cosmic web we observe today is a snapshot of the dark matter distribution in the early universe. This mysterious dark matter acted as a hidden hand, guiding the growth of galaxies. Exploration of this unknown new universe necessitates the discovery of the laws of physics underpinning the fundamental particle nature of dark matter. The James Webb Space Telescope may have shed new light on the dark universe. Some of the telescope's recent pictures have turned up 3 potential dark stars, ones powered by dark matter, the invisible stuff that makes up most of the matter in the universe. Scientists first proposed the existence of dark stars in 2007. The idea came from a team led by Catherine Fries, a cosmologist who studies the universe at the University of Texas at Austin. According to Fries, if dark stars exist, they would be very weird looking. The Sun and other normal stars make light and heat by smashing hydrogen atoms together under immense pressure. When these hydrogen atoms fuse together, forming helium, they give off lots of energy. This process, called fusion, powers all the stars we see today. In contrast, dark matter would power dark stars. Scientists aren't sure precisely what dark matter is or how it works. We know only that it exists because dark matter's gravity tugs on stuff we can see, such as galaxies. But it's possible that dark matter can also interact with itself. When two dark matter particles collide, they could destroy each other. Like fusion, that annihilation could produce enough light and heat to power a star. Dark stars can't form today, there's just not enough dark matter around. But these celestial bodies might have formed in the infant universe, perhaps a few 100 million years or so after the Big Bang. Dark stars would have formed from clouds of hydrogen and helium. Gravity would have drawn these two elements together along with any dark matter nearby. As the dark matter particles got closer, they would start annihilating. When dark matter particles collide, they produce heat. This heat prevents the cloud of hydrogen and helium from collapsing completely to form a normal star. This process is similar to how heating the air inside a hot air balloon keeps the balloon inflated. Unlike normal stars that compress into tight balls of gas, dark stars would not, allowing them to grow to enormous sizes, up to 10 times the width of Earth's orbit around the Sun, which is over 2,000 times the width of the Sun itself. The largest dark stars could be millions of times as massive as the Sun and billions of times as bright, potentially bright enough to be spotted by the James Webb Space Telescope. This telescope, which orbits Earth, looks for very ancient, distant objects. To find dark stars, Catherine Fries and her colleagues searched the catalogue of objects that the James Webb has identified as being from nearly 14 billion years ago. They found adequate data on electromagnetic emissions for only 9 of these objects. Of those 9, 3 matched what scientists expect dark stars to look like: Jade, GS, Z13-0, Jade, GS, Z12-0, and Jade, GS, Z10-0. These objects had high redshifts, indicating they emitted light skewed toward the red end of the electromagnetic spectrum, a sign of old and distant objects. The light also appeared to come from a single-point source, such as a star, rather than a fuzzy galaxy. These 3 real-world objects matched scientists' expectations of dark stars, which is remarkable. Detecting dark stars would provide new evidence of dark matter and could hint at how this mysterious substance works. Tracy Slatier says that knowing dark matter could annihilate itself would be powerful. Dark stars might also explain the origins of supermassive black holes, which have millions or billions of times the mass of our Sun and sit at the centers of many galaxies. Smaller black holes can form when giant stars die and collapse, but the formation of supermassive black holes is less understood. Once all the dark matter in a dark star has annihilated, the remaining hydrogen and helium cloud would collapse, forming a massive black hole. These giants could merge over time into supermassive black holes. Thus, our journey into the cosmic dawn continues with the James Webb Space Telescope guiding us. Each discovery brings us closer to unveiling the secrets of the early universe and understanding the forces that shape the cosmos. The high redshift galaxies observed by James Webb serve as time machines, allowing us to peer into the past and approach the enigmatic origins of our universe. The cosmos unfolds its mysteries, and we, as explorers of the unknown, stand at the brink of discovery. In other news, scientists using a NASA space telescope have discovered a tantalizing world. About the size of Earth, it sits remarkably close to our solar system and could be comfortable for life as we know it. The exoplanet, named GJ357d, orbits a small and cool red dwarf star located just around 40 light-years from Earth in the constellation Pisces. The exoplanet, found with NASA's Transiting Exoplanet Survey satellite, TESS, is estimated to have a width around 1.1 times that of Earth, making it similar to our planet as well as Venus, often called our solar system's twin. GJ357d orbits its star so closely that its year lasts just 12.8 Earth days. However, because the red dwarf is about a quarter the size of the Sun and much cooler, GJ357d is still in its star's habitable zone, or Goldilocks zone, where conditions might be just right for liquid water. Though the researchers can't yet confirm if GJ357d has an atmosphere, they are cautiously optimistic. Lisa Pallett, a scientist at University College London, who co-led the research with University of Southern Queensland astrophysicist Shishi Odekori, noted that the majorly interesting thing is that this planet is really nearby, one of the closest transiting planets to Earth. It's either in the habitable zone of its star or right on the edge, so it could be habitable. Scientists spotted GJ357d as it transited, or crossed, the face of its parent star, causing tiny dips in light that TESS is adept at detecting. Pallett added that finding the planet's size to be similar to Earth's was a lovely surprise, and its potential habitability between Earth and Venus is really exciting. GJ357d receives about 85% of the radiation Venus gets from the Sun, but has a much cooler surface temperature of 107 degrees Fahrenheit 42 degrees Celsius compared to Venus's 867 degrees Fahrenheit 464 degrees Celsius. Though Earth and Venus are both in the Sun's habitable zone, one supports life while the other is inhospitable. Studying GJ357d could help us understand why. Pallett and Van Eisen plan to investigate whether GJ357d has an atmosphere, but early indications suggest it might be thin. Surprisingly, a thin atmosphere could be good for habitability, as thick atmospheres of hydrogen are typically bad news. Red dwarfs, the most common stars in our galaxy, comprise about 60 to 70% of the stars in the Milky Way. Understanding planets around red dwarfs, which burn at lower temperatures and have much longer lifetimes than stars like the Sun, is crucial. Despite their cooler temperatures, red dwarfs are highly magnetically active, often emitting powerful flares that can strip planetary atmospheres. However, GJ357d's star is thought to be relatively calm, improving the exoplanet's chances of having an atmosphere. Detecting exoplanets around red dwarfs is easier due to their smaller size and cooler temperatures. To investigate GJ357d further, scientists will use other instruments and methods, like the radial velocity method, which measures tiny wobbles in a star's motion caused by orbiting planets. They hope to be granted time with the James Webb Space Telescope to examine the planet's atmosphere using transmission spectroscopy, which identifies atmospheric elements by analyzing starlight passing through it. GJ357d, one of a few temperate Earth-like worlds close enough for such study, offers a promising start for exploring life beyond our solar system. As Pallett concluded, while we can't say anything for certain yet, GJ357d will teach us a lot about life, making it an exciting subject for future research. That's all the information for today. If you enjoyed today's episode, please give us a thumbs up, subscribe if you haven't already, and hit the bell to never miss future episodes. Tell us what you think about today's content. Your support motivates us to continue delivering quality content and always improve. Thanks for watching, and we'll see you next time.